Thanks for joining us for another episode of DPC Radio. This episode was recorded live in Amsterdam at the Dutch PHP Conference 2012. For more information about the Dutch PHP Conference, visit our website, phpconference.nl.
Okay, so I'm going to get started because I have about an hour's worth of talk to get through, and we obviously don't have that long, so hopefully I can fit it all in. This is Fast Not Furious, How to Identify and Fix Slow Code. My name is Davey Shafik. I am an engineer at Engine Yard working on the Orchestra platform as a service. I am the author of these 3 books, contributor to Zen Framework, PHP Doc, Frappy, PHP Internals, a whole bunch of stuff. At dshafik on Twitter. Can everyone hear me, by the way? Okay. And please buy my books, because those are what allow me to come here, as well as Engine Yard. There is one more really important thing, which is that I am hard of hearing. So if you have a question, I will probably come out and listen to you in the audience, as opposed to having you yell it out. So a little bit about these slides. I try to do something that hopefully makes it better for you, which is that I make 2 slides per section. I have a title slide like this one for when I'm talking, and then I have a detail slide, which will be in the handout. And I'll just skip through those, and I use those for my notes here, so you guys aren't reading what I'm saying, because that's really boring, right? So that's what I'll be skipping. So there's a saying by Jeff Atwood, which is, hardware is cheap, programmers are expensive. There's one caveat that I add, which is only if you respect the hardware. So at my previous position, we had a long-running script that took about 2.5 gigabytes of MySQL data and transformed it into another schema and threw it into another database. Same server, so there was no network latency. And it took about 10 minutes. It was pretty fast. And then we changed the schema, and we added some indexes and made some performance tweaks. And one of those tweaks was that we added GC collect cycles, something that was added in 5.3 to collect memory. So we weren't chewing up so much memory. We were using a lot of objects. And we just stuck it in there and moved on. And suddenly that 10-minute script took 8 hours. And we were looking at our performance, and our MySQL queries would start at 3,000 per second and then drop steadily until they were at 3 per second within about 20 minutes. It took us forever to figure out what it was. We just assumed it was memory or the database or whatever, and there was nothing else that looked slow. So we profiled it, and it turns out it was the garbage collection. We took that out and we went back to 8 minutes. So it actually got faster with all the other stuff that we'd done. So the reason I say that is to be very careful when you're doing optimizations. Always test your optimizations. It's very easy to get it wrong. To the detriment of we spent weeks running this 8-hour script, one a day. It's forever. So common causes of slowdowns, databases. It doesn't matter whether that's Postgres, MySQL, Mongo, all the NoSQL stuff. They're a very common cause of slowdowns. The number 2 is external resources. APIs are becoming more and more common, but people are not being sensible with caching those results and just blindly calling them like they're a database. And file systems are huge. But don't forget your network I/O and your external processes if you're doing anything like exec or something like that. And then the number 3 reason, which is the one we're going to look at today, is bad code. It's a very minor reason normally. And I have a saying, which is, there is no great code except code that never has to run. Everything else is just good code. So the first question that you're going to want to ask yourself is whether or not you even have a problem. A lot of us kind of assume that our code is slow. We run it on our local boxes, and I've got a MacBook here. It's not exactly a beefy machine. So the number thing that you want to do is find out if you even have a problem, because premature optimization is the devil. Nobody wants to do that. So the way that you're going to do that is determine your desired performance. What is it? And typically you're going to be looking at number of concurrent users with an expected response time. So say 100 concurrent users with responses in 1 millisecond. Once you've decided that, you're going to benchmark. And you're going to want to do it against close to production hardware. You can't do it against your local box. Until you determine that what you're shipping is not going to work for you, then you're kind of working against yourself. So once you've got your benchmarks, you then know if you have a problem, and most importantly, how big the problem is. So we're going to look at the performance loop. It's a very simple loop. Benchmark, profile, then make changes. and this is the common question I usually get, isn't profiling the same as benchmarking? It's not. And the big difference is that profiling records the relative speed of any given function, its memory usage, the number of calls per function, and the call graph. The act of profiling itself actually affects the speed of the code. If you've ever run Xdebug in your production systems, you know you can't do that. It just is too slow. It's a bit like quantum physics. Observing it changes the result. So benchmarking tests actual speed, what your users are actually going to see. And you're going to want to look at things like JMeter, AB, Siege, those kind of tools for benchmarking. So today we're going to look at profiling with XHProf. So we've determined that we have a problem. We kind of know what performance metrics we need to make up. We're 20% slow, 30% slow, whatever that is. So we're going to look at XHProf. Has anybody used XHProf yet? Okay, so XHProf is a new tool from, it's not that new, it's about a year old, from Facebook. And they actually have it installed on their production boxes. And they randomly pull metrics from actual production nodes, and they look at it over time. It's a really powerful tool. So it's in PECL, so it's open source, it's part of PECL. And to install it, unfortunately, the PECL command doesn't work at this present moment. So we install it just like any other extension. So we grab the tarball, we extract it, go into the directory, and then configure, make install, just like with PHP. And then update our PHP INI, and then restart your web server, FPM, whatever you're using. And that's it. It's a really simple install. But there's another part, which is XHGUI. And this is really where the benefit of using XHProf comes in. Who's used Xdebug for profiling? How many of you use a Mac? Have you run kcachegrind on a Mac? Kind of a pain. And kcachegrind is a far better tool than WebGrind. WebGrind is okay, but kcachegrind is great, but it sucks on the Mac. So XHProf is all web-based, this GUI, and it's a better tool, I think, than kcachegrind and anything else. So this is an extension by Paul Reinheimer. It's available on Git, so you just clone it. I'm really skipping past these parts because all the actual details come. So clone it, you go into utilities, you set up your database connection by throwing a class. There's like multiples, like MySQL, MSSQL, that sort of thing. So you symlink in the correct one, you import the database, and then you modify the config. Not very difficult. And the last thing you do is set up a virtual host. So once you've got it all installed, you need to use it. And this is done in PHP. It uses auto prepend and append files. Anyone use that for caching with obstart, obend, that kind of stuff? So basically you just add the prepends either in your virtual host, which is nice because you can do it for one virtual host on your dev box, for example, or in the PHP INI, and that's it. It just works. You hit the code with underscore profile equals 1. It sets a cookie, and it will profile from that point on until you pass in equals 0, and then it'll stop. So you can actually request a page that requests dynamic resources like dynamically generated images and such, and it will profile all of those as well. So we're going to look at a demo. So I'm going to switch out of my slides and switch to here. So what I'm going to be demoing for you is profiling of Frappy. Anyone here used or heard of Frappy? Okay, so Frappy is a REST application framework, and it was a very poor choice for this demo because it doesn't actually do much. And it was a great example of not over-optimizing. So I'll walk you through the problems I had trying to get this demo put together. So this is a Frappy page. We're hitting a web service, and we're getting a JSON string. It's not technical. There's no database stuff involved, which is one of our major slowdowns. There's no disk I/O, except for config files, PHP stuff. So I'm going to go ahead and refresh that. Let me just, make sure I've got everything clean first. Okay. All right, so I'm going to go ahead and refresh this and switch over to XHProf. So this is the GUI that we're going to be working with. This is the XH GUI. And there's not much to it until I refresh. Please work. Live demos are great. Okay, so this is a single request. Every request that happens to PHP with the profile stuff on will show up here. If you look, it's a little bit doesn't quite fit on the side, but you can see the last 25 or last 50. That's just the last 50 of any script, but you can actually see over time for a single script backwards pretty much forever, just not in this list. So there's a couple things going on here. If I can find my mouse cursor. This is to go through to the information, which I'll do next. And then these are to see over time statistics, which we'll get into. This is where I think all the power in XHProf lies. So let's take a look at what actually happened while profiling. So this is our run. This run ID here is something you're going to want to take note of. You may need it later. Of course, it's not going anywhere, but I'm just letting you know it's there. And basically, we have a whole bunch of information here, which I usually ignore. Mostly, I go down to this right here. This pie chart is it groups a whole bunch of stuff together, but it's an overview of where all the time was spent in our profiling. So we have our other, which is all the little stuff that kind of added up to this big chunk, and this here, which is our obvious bottleneck, loading. So what is loading? Basically, it's a group inside of XHProf, which includes require once, include once, require, and include. So it's loading of PHP code. This is not loading of external resources or anything like that. It's just PHP code. So if we come down here, we now get a breakdown of everything. These colors down the left-hand side correspond directly to these colors, which is kind of nice. And then we have all these different columns. So this is the function that was called. It shows you the class and everything. It's the full qualified name. We have the number of calls, which is very important. It doesn't always correspond to the most used function, but very often it's a good indicator of stuff you are doing wrong. The wall time is literally the number of seconds on a physical wall clock. It's not the CPU time, which is how many seconds or microseconds the CPU spent on it. This is the CPU time, which I typically ignore because it's based around like scheduling and stuff on the CPU, and it's not, for me, it's not as important as wall time. Memory usage is the peak memory usage of that given function. Memory usage is the total memory usage of the script. Peak memory usage, I hate these columns. Skip that one. Exclusive wall time, that's the important one. Okay. Exclusive wall time is the amount of time spent exactly in that function, not all of its child functions. Okay, so you can see why did you do that? So you can see that main took the entire time of the script because that's how long it took. But actually doing anything at that level only took this tiny fraction of a second. And there is more here. This is the amount of CPU spent directly in that function. Memory usage, at the end of it, there was none left, so it got negative. And then the peak stuff again. So this is pretty good, but once you do this twice, you then get a better look at actually where all of your time was spent. So now we're ordering by wall time, and we actually want to look at this case in the tree, the aggregate, so how the children and stuff went. So we're seeing exactly what we saw in the graph, which is this file here, which all it does is include a whole bunch of files, takes the longest time. So that bears this out right here. Let's take a look. We'll click through to that. And most of the time was spent with all of these loads right here. There's just so many of them, they add up to a lot of time. So there's a very simple way to get around this, and that's to use APC. Anyone not use APC? One person. Okay. APC is a bytecode cache, and it will basically stop you from loading files off the disk if they've already been loaded and haven't been modified. So what I'm going to do is go ahead and turn on APC. Sudo. Okay, restarting my web server. And I'm going to go back and re-hit that same page and go back to my listing here. Now you'll notice it took exactly the same amount of time. That's because it never cached yet. So we'll hit it one more time and refresh again. And we dropped a whole bunch of time. This is great. Not quite as much as I was expecting. I was kind of expecting almost half of that pie to disappear. Let's go take a look at why. That's not actually this object. Refresh that. There we go. So there's a whole bunch of loading still happening. This is the problem with this live demo, because obviously it's very dependent on exactly what I'm doing on my box. But there's still a whole bunch of loading happening. And the reason for that is that we're now running a different code path, and we're still loading different files because of that different code path. It's just something that Frappy's doing. Yeah, it happens, but it's fine. The biggest, except for the other, which we can ignore, the biggest problem that we see is a call to isObject. Why on earth is that a performance hit? So I went and sorted by wall time. And I see all of these make array calls. These are different iterations. It's a recursive function. So if I go into the most bottom one, which is this one right here, and I can see that isObject is taking up over 50% of the time in this function. And I know it's a recursive function. So array map is only taking up 5.3% of the time. That doesn't seem right. So I went and pulled up the code. And I won't do it right here, but basically what the code is doing is it calls isObject twice. The first time it checks if it's not an object, then the second time it checks if it is an object. But the first time, if it returns false, it bails out of the function and never gets to the array map, which is why we have 131 calls to isObject and only 14 to array map. So we end up with this really skewed set of numbers. If we go read the code, we understand why, and actually this is fine. So this is kind of a misleading for us, but it's good for us to know. One of the other really cool things in XHProf, I'll just quickly throw up here, is the call graph. For this one's not too big. So this is the actual call structure, the stack. You'll notice certain things are highlighted. So here we are, that big red one. That's the slow one. It's nice and easy to kind of find things that way. So this is kind of interesting, but this is not the number one most powerful thing about XHProf. What's really cool are these two little tiny links here, which actually correspond to these two links right here. So what's the difference between these two URLs? If you look very closely, you'll see that one of them has collection 2, siblings 1, foo equals bat. And then this one has all of those kind of numbers and variables replaced with x's. Because very commonly, especially in production systems when you've got different users logged in testing different things, those variables change, but the code execution path is the same. So we store both. So I can take a look at this one right here, and I can see all of the overtime statistics for that exact set of variables. So say you notice that when somebody passes in bad, it goes slower than when somebody passes in something else. You can find out exactly what those differences are, look at the code paths, and realize, oh, it's because when it pulls that set of data, it hits a different relationship in the database at the end of the day and does a whole bunch extra work. If we go back one more time and click on this one, it's going to be the same data because we've only hit the same thing. But this allows us to look at the generics. So with any set of data, it'll go through this one. And that is achieved. I'll show you. There's a function called Earl Simulator, which allows you to mangle the URL as it's being stored in any way that you want. It's part of your config file, and I'll show you the one that did this. So there's 3 different parts to this graph. Each dot is a run, sort of in a line, and we have the CPU, the wall time, and the memory usage. So what we take away from this graph is that when we added APC, our memory usage went up because we're storing all of our opcode caches. This makes perfect sense. But our CPU time here came way down. It's great. And then on the second run, came down even further. And our memory usage, because we're not storing all that stuff, we're only pulling in what we need at that point, and we're only pulling in the opcodes, not the whole code, goes way down as well. And this is the trend that we obviously want to see. Let's go back here. So I'm going to look a little more at what was causing all that problem. So as I said, the only good code is code that never has to run. How do you have code that never has to run? You cache the output. Doesn't matter whether it's SQL, doesn't matter whether it's PHP. So improving this was impossible. I assigned the isObject to a variable as opposed to calling it twice, and I went from 50% of the time to 47% of the time, and it gained me half a millisecond. It was useless. So let's make it not run. So we'll go ahead and switch back to my terminal, and Php custom all files, and we'll go ahead and turn on caching. Now, Php has a whole bunch of adapters, but APC is the default. So I'll go ahead and enable that and run again. And go back to our list, refresh, and it got slower again. And this is that whole case of it takes time to cache, so the first time kind of sucks. So we'll run it again. You got to be very careful of those false positives. You also have to clear your cache to make sure you're still getting them. And this time it jumped way down. The best code is code you never have to run. Okay, so we can then compare. Grab this, and this is what I said is important. We'll grab that right there and compare it right down here to this other one. Not that one. Oh, that's fine. This one was before the cache. And we'll take a look at the delta. So I said that information was kind of useless. It's not. This is where it comes in important. So we can see that with the first run, we ran 1,155 function calls. Once we cached, we were down to 355. That's huge. It's 800% saving. We can see our wall time drop way down, but we saw that before. Memory usage here is another great indicator. It's not so big here because we're not using much, but it's still pretty cool to see. Also here listed, you can see the different variables. This is great when you're looking at two completely separate runs and not looking for like cachy stuff. So you can actually compare what happens when you pass in two different variables in this sort of delta view. And then this is the post data would be listed here. There isn't any. And then right here we have the same list of functions and everything, but it tells you the difference. This is how much faster or slower the second run was to the other one. So it's still a delta. I really wish if I could, maybe if I can't really get it to. Looks a little better on your screen. If the guy who did this UI had gone to Mike's talk, he might look a little better. So the two major things that are great in XHProf is the comparison stuff I just showed you and the overtime stuff and these similar stuff. This is wonderful to see. So I want to show you how the simulator stuff happens, and I have it. Do I have it on the slide? I do. So basically, this is done on write time. At the end of the request, XHProf GUI writes to the database, passes the URL into this function, and again, it's in your config file, so you can define whatever it is. And I just have a quick prereg replace for numbers. Any number gets replaced with an X, triple X, sorry. And then I blow up the query string, replace all the values with X's, and build it together and throw it back on the end again. It's a really simple function. I wrote this at about 4 o'clock in the morning on Monday, Tuesday after being jet lagged. So I don't know if it's any good or fast. I need to profile it. I need to profile XHProf. But it works, which is the important part. But being able to do this genericizing is great because we do hit a lot of those same URLs and they're running the same code paths, and you can actually still do the comparison. And as I say, it's really good that it doesn't lose the unique values because sometimes it is important. Any questions on XHProf or anything you want to see, anything I missed? Okay. So as I proved, caching is great. Any code you don't have to run is great code. And all caches are key value stores. And there's a bunch of them. There's APC, which has a whole bunch of limitations, but is really simple for simple projects. Memcache is my personal favorite. Cassandra, Redis, and then most NoSQL stuff kind of qualifies, but now is kind of getting slow. Anyone not using one of those I just mentioned? Anyone not using caching? Okay, that's good. Same guy who's not using APC. So we're going to look at Memcache. As I said, it's my favorite. Memcache is super simple. You have a key and a value, and you store it in there, and it distributed clusters, and it's stupid simple. But I came up with this technique called namespacing. And this came about because at my previous position, we had 250 clients on a multi-tenant server, and we were putting everything in Memcache. And when somebody made an edit, we blew away the Memcache cache, which meant that 250 clients lost their data, even though one client made an edit. And that was a very bad mistake. Also, clearing a gigabyte of Memcache is not the fastest operation. It's not too slow, but it's not necessarily the fastest operation. So we came up with this idea of namespacing. So namespacing is basically creating containers within Memcache using your keys that are boxes. And what's really great is you can have one namespace and fill it up and then go, I don't need that anymore, and create a second one. So what we did is we created a key in Memcache. Our namespaces are stored in Memcache, and it's seeded with a random number. And if the value doesn't exist, we just do rand 1,000 and throw a random number in there. And then we pull that key every time we want to set something in the cache. And that key is going to be based on a grouping of some sort. Doesn't matter what. We use client names. But for you, it could be part of your application. We pull that number, and then we create a unique key that includes that number. So for us, it was Cornell _ whatever that number was, and then a unique key for whatever the data was, which would be reproducible. So it's a SQL query, for example. Hash the SQL query. No matter what namespace you're in, that hash is always going to be the same for that SQL query. And all we had to do to clear the namespace was increment the number, which meant that it was no longer the same key once you put it all together. And I'll just show you this slide because it kind of makes a little more sense. So we seed it with the Memcache set, and then we end up with this. I don't know if I can get my shadow right, but we end up with this my namespace _189 _ and then the hash for the SQL query. And then when we want to get rid of all the cache in 189, we bump it to 190, and that key is no longer valid. So next time we try to pull the data, we look for 190, there's nothing there, we store it. So taking this just a little bit further, we brought in segmenting. So we subdivide our namespaces. And that's done pretty much the same way. We create another namespace, which is based on the first one, seed it again, and then to generate the key that we end up with, we use the first namespace, followed by the second namespace, and then the hash. What that means is that where that 4 is, which is our my namespace config key, we can increment that to 5, but leave the 189 alone, and all we're changing is anything that's in that subset of keys. So what that looks like, is we pull in our cache memcache class. We're using the request URI as the key because we're just caching front-end pages, for example. We go ahead and try to pull based on the key, and we have our namespace of blog pages. Doesn't find anything, it stores it. Otherwise, if it does find it, we echo it out. Otherwise, we go ahead and create it. We do an obget flush, which will return it and output it at the same time. And then we cache it. And again, we're using this blog pages namespace. So what we could actually do is have a blog namespace, which is everything. So say you install, say it's WordPress, and you upgrade WordPress, you want to clear every single cache, we can just blow away the blog namespace and all of the caches are clear. We don't need to go through all the different individual segments. But if you write a web page, or you write a page or a post, we'll blow away blog pages or blog posts, or you make a config change, blog-config. And this is how we clear the cache. So this is going to, instead of calling memcache clear cache, it actually does our increment. Any questions on this whole class, this cache memcache, I'm going to put a link in the notes and actually throw it up in a gist. Any questions on this stuff? Okay. How am I doing for time? Okay. So as I mentioned, APC, use it. There's no reason not to. And I wanted to go a little bit deeper into APC because a lot of us use it but don't really know how it works. I think it's kind of important. So we're going to look a bit at internals, or here be dragons. So we're going to look at the worst hello world ever, which is this huge greeting class with a method that's say hello and a variable. Anyone not get this code? Pretty simple, right? I've actually got my slides mixed up. I want this one first. So most people say PHP is not compiled. It's a scripting language. It's not compiled. It's not strictly true. What we do is we compile it every time it's requested. It's not great, but that's what opcode caches are for. But how do they work? So the actual PHP lifecycle is very similar to the Java one, except that rather than compile it first and then end up with this binary file, which is the set of opcodes, or as they call them, bytecodes, which we then later run, we do it on the fly. So we just skip a step. With an opcode cache, we get closer to the Java scenario. The first time you do it, it's like running the compile, and then that's stored in a binary format, and the next time we're running from that binary format. So we call the PHP script, it checks the opcode cache. If it's not cached, if it is cached, it just reads the shared memory, runs the code, and it's done. If it's not cached, then it'll parse it, compile to opcodes, which is the previous, same as this one, and then does the one extra step of saving it to shared memory, so that the next time we run, it's there. So what are opcodes? That tiny little bit of code turns into all of this junk. Every opcode, it's called a token, the other name for them, starts with a T, and then there's a whole bunch of them. And down to open tags. You'll notice there are some lines without an opcode, like, for example, the curly braces. They were very smart when they wrote this, that if the opcode would be longer than the thing it represents, they just use the thing it represents. So that's parentheses, braces, and quotes, and semicolons. None of those have opcodes. White space, however, does, because it may be a single new line. It may be who knows how long, right? So if we actually follow this down, you can actually see the entire code taking place. Class greeting, open the class. Public function, say hello, the variable argument. Open the brace for the function, echo hello to. So this is the exact same code. This is a whole bunch of stuff this is not quite, but almost exactly what gets stored. It's stored in a binary format, but what gets stored by APC. The main thing that APC does, in addition to caching this information, is it will actually look for logic branches that don't make sense. So say you have if false, it'll remove that entire set of opcodes. Saves memory, doesn't even have to look at it. It's a no op. That's the one other thing that APC does. So when you're running code, this is what's happening. Now, the way I got this information is I used the tokenizer extension. I wrote a tiny little script. Let's see, cdu docs, no, docs. 2012. What, really? Tokenize. How do I get rid of that? Anyone know how to get rid of nerd tree? All right, there it is. Literally token get all, throw in the source code, iterate over it, and then there's two types of tokens. There's the ones where there's an integer that represents the string token name, which is retrieved through token name. You can see it kind of here. And then the ones that don't have token names, their first value, it's an array. Their first value is the actual token. So that's why you have the if-else. So that's all the code I used. There's also something called VLD, which is by Derek Rattans, who does Xdebug, that can dump this kind of information, but this is easier for me. That's an extension in Beckle, again. Let's see. All right, so did everyone get all of this stuff? I went through that kind of fast. Okay. So installing APC for that one guy over there, Beckle install APC, add extension apc.so to your INI, and you're done. Why are we not using it? I think that leaves me with time for a few questions, if there's any. Yes. Oh, hang on. Yes.
XHProf,
Yes.
it adds a performance penalty to your service?
It's very, very minor. As I said, the way that Facebook does it is like 1 in a million requests gets profiled, so it's random. I have used it in production and not really noticed a penalty. The performance penalty versus Xdebug is like maybe 10% at most of what Xdebug had. So it really depends on your setup. It's not noticeable normally. It kind of depends on other stuff that's going on. I think that the random activation is probably a good compromise. But throwing it on your staging boxes and on your QA boxes is not going to slow down your teams looking at those things. So, anyone else? Okay. Guess I'm finished early. Thank you.
DPC Radio is a production of iBuildings. The materials presented are copyright of the speakers. This episode is released under a Creative Commons Attribution, Non-Commercial, No Derivatives 2.0 license. iBuildings is a full-service web development company specializing in PHP development. For more information on how we can help you with your next web project, visit our site at ibuildings.com. Thanks for listening, and we hope you'll join us again for DPC Radio.